Hello everyone, this is Full Academy AP Chemistry class. Today we'll continue to learn the quantum mechanical model. In the last lesson we stopped at the brief introduction of QM model. It comes from Schrödinger's equation and only determines the probability of finding an electron in a particular space. In this model, atoms look like a cloud with no boundary. But obviously, regarding an electron as an infinitely huge cloud is very inconvenient to study, so a new concept is defined. An atomic orbital is represented pictorially as a region of space in which there is a high probability of finding an electron. More specifically, the orbital surface contains 90% of the electron's total probability distribution. The higher energy an electron has, the bigger the orbital will be. Now, since some people might be confused with orbital and orbit, let's quickly compare and contrast them. Orbits are proposed in Bohr's model, while orbitals are in QM model. Both models involve the concept of quantized energy, which means that the energy of electrons are restricted to certain values. Orbits define the paths for electrons, but orbitals are regions of space, and they only describe the probability of finding electrons. Energy is central to QM model. The major energy level, or we can remember it as the primary categorization, is the principal energy level. Principal quantum number specifies the atom's principal energy level, and this number is written as a lowercase n. One principal energy level may contain several energy sublevels that are slightly different in energy, and the number of sublevels and principal energy level has always equals to n. Sublevels also have names and different shapes. From lower to higher energy, we name them S, P, D, and F, all written in lowercase, and they are the shapes of them. Now you might ask, where's the orbital? Well, sublevels have various numbers of orbitals, and they have different orientations. Sublevel S only has one orbital, which makes sense because a ball cannot have more than one orientation. P has 3, D has 5, and F has 7 sublevels. Each sublevel is labeled with quantum number n and the letter of the type of sublevel. So if we rank sublevels from lower to higher energy, it will look like this. 1s is smaller than 2s, smaller than 3s, and smaller than 4s. 3s is smaller than 3p, smaller than 3d. Orbitals within one sublevel have equal energy. Here's one graph to illustrate this model. I don't mean that the atoms of this model looks like this, but I think it will be easier to remember the relationship of everything. A maximum of 2 electrons can be held in one orbital, and the orbitals are parts of sublevels. Sublevels are involved in the principal energy levels. This is the numerical relationship of them. Lowercase n represents quantum number. It also determines the number of sublevels. N squared indicates the number of orbitals in one principal energy level. For example, the third principal energy level has S, P, and D, 3 sublevels. The total number of orbital is 1 plus 3 plus 5 equals 9. Then if we double the n squared, we get the maximum number of electrons in one principal energy level. In conclusion, one electron can have 90% probability to emerge in its orbital. If energy increases, the size of its orbital will increase and the orbital's shape will change too. But orbitals in one sublevel have equal energy. I can understand that some of you might still be unclear about all this stuff, but it doesn't matter. As long as you remember all the concepts, you're fine. Maybe after we finish learning electron configuration, you can fully absorb all the knowledge, because we'll reveal them from a different perspective. The definition of electron configuration is the way in which electrons are arranged in the various orbitals around the nuclei of atoms. It describes which orbital the electron occupies and what energy it possesses. It also determines the chemical properties of the element. We'll learn 2 principles and 1 rule about electron configuration in the next lesson. That's the end of today's class. Thanks for listening. See you next time.